All right, so you should, if you did the, what is this, the third exam, right? If you have that for me, there you go. Thank you. All right, couple of administrative things first. Your work is awesome. Did you get that note on my last one?
Yeah.
Okay. I meant to ask you if I could show the class like the order of things, but we'll talk later. Okay. I mean that like neatness, like the way you present something. It's kind of what I'm going for. All right. We have an exam a week from this Wednesday. So next Wednesday is the last Wednesday before spring break, right? So we have our midterm. Remember, we only have a midterm and a final. So I would expect for me to give you some sort of guidance, some sort of review for that exam here in the next day or so, all right? And then you also have a mini exam that's due when?
I think it's next Wednesday.
Is it also on the 8th? Yeah, so, hey, you know, it's the way things lay out. So I had jury duty this morning, and they're still on the Zoom way of doing things. They're about to stop doing it. So instead of going down to the courthouse, I got onto Zoom at 8 o'clock this morning, and then I had already answered an online questionnaire, you know, all about me and my education, all this stuff. And from that information, I got selected to be on the panel, which now has to report physically to the courthouse. And it was either going to be on Tuesday or Wednesday, and it turned out to be Wednesday, which is 2 days from today. So I've got to go downtown, and I don't know what's going to happen that day. So we have to decide this Wednesday what we want to do in terms of class. We have two options. Well, yeah, two options. Option one is that I basically ask you to maybe watch some video online. We're a little bit ahead right now. Like today is we're supposed to be, wait a minute, today is, yeah. We're supposed to be doing chain rule and directional derivative today. We're finishing directional derivative today. We're finishing it. So we're like a day ahead. We could, if you want, I could have you watch a video on Lagrange multipliers to kind of like get you acquainted. This is a hard section. The section's really tough. So I could have you just like watch a video, and it wouldn't be on your midterm or anything like that. Nothing on Lagrange is on this exam. So it'd just be a way for you to just do something, right? But at the same time, it would be us kind of like relaxing a little bit, right? The other option is to actually have class and have a sub come in. But I, right now, don't even know if I can find a sub to do Cal 3. You know, there's one or two other faculty that teach Cal 3, and I don't think they're available at this time slot. So it'd be tough for me to do that. So how do y'all feel about Wednesday we doing just like me give you an online assignment? Is that okay with everyone? That's okay? Any objections? Anyone really want to have a sub? No? Okay, if you don't, you do? Oh yeah, whatever we cover here, I just want you to preview it. So if I give you an assignment, it would just be so that we could get through. What you need to see with Lagrange are a lot of examples. Because what gets people with Lagrange is the algebra. The algebra of the Lagrange is tough. And knowing how to write things down and knowing when you're done. Like it's hard to tell in Lagrange when you're done. So the more you see, the better. So it'll just be like a preview of it. And then we'll do more in class. So everyone's okay with that? If you have any objections that you don't want to state now, just send me an email after class and state your case. But most likely we're just going to do an online assignment for Wednesday. And then hopefully I won't get picked for like an actual like long drawn out thing. We have a couple of strategies, right? So I might try a couple of things when I go in there. No, we were talking about you go in there like, holding a Bible and like, pounding, or you could
say that you don't believe the law is, what is it, ethics?
Yes, whoa, shit. Something like that, all my
This morning about how to get out of jury.
yeah, I'm on camera, I should probably shut up before we, okay, let's talk, I just mentioned a lot of important stuff, so talk to me after class. This is off topic, not that we have time for this, but some of my colleagues said that I should share this with y'all because you might find it interesting. How many of y'all have seen the Fibonacci sequence before? Yeah? Okay, so it's just a sequence that what you do is you always start with the numbers 1, 1, and then the next number is the sum of the previous two. So 2 comes from adding 1 and 1 together. 3 comes from adding 2 and 1 together. 5 comes from 3 and 2. 8 comes from 5 and 3, and so on and so forth, right? So the next number in the sequence would be what? 34, right? It's these two added together. Yeah? Okay, now if we take this, there's all these different weird things that happen with the Fibonacci sequence. One of them is this thing called the golden spiral. I don't know if you've ever seen this. But the way it works is you start with the number 1 and you draw a square. And I'm going to label that square 1. And what that means is not that the area of that's 1, but I'm telling you that the length of the sides are 1. So this is a 1 by 1 by 1 by 1 square, right? And then what I'm doing is I'm going to draw, my next square is also going to be a 1 by 1 by 1. So I put it here. And then the next one would be a 2 by 2 by 2 square. So I'm going to put that like that. Put a 2 in here. Do y'all agree that that's 2? Because that's 1 and that's 1, so that's 2. And then the next one is a 3, so that would be, right? So that's 2 and that's 1, so that's 3 by 3. And I could keep doing this, right? Go down here, oops, that'd be a 5. So 3 and 1, that's 5. And just keep drawing this, right? All these squares that go around. That would be 8, right? And then this next one would be 13, one last one, the one over here, 21, right? And now what you can do is you start with the very first square, you start in the top right corner, and you connect the corners with an arc, and you continue to do that across the corners of each of the squares, connecting corner to corner with an arc, and you get this thing called the golden spiral. And it appears in different places in nature, and that's actually debatable, but you know, there's a bunch of things that you can look into with this, right? So the Greeks really thought that this was something fascinating, and they believed that if you start looking at this, like just look at this right here. This is a rectangle, isn't it? And when I draw the next square, I'm going to get another rectangle. And the next square, another rectangle, and they get bigger and bigger. The Greeks believed that the rectangle you're seeing is kind of approaching this like perfect, like most beautiful rectangle. And so they based a lot of their geometry and buildings off this perfect rectangle. And like one example of a rectangle, let's say this is a 3 by 1 rectangle. Then I would say that the ratio here, if you take that side, divide by this side, right, you get 3. This ratio of the height to the width would be 3, right? The Greeks believed that the perfect ratio, let's call this y and let's call this x, they believe that the perfect ratio, if you take the y and divide by x, that perfect ratio is the same as what you get if you take this number, divide by that. If you do it on your calculator, whatever that number is, that's what the Greeks believed was the perfect ratio. And if you do this on your calculator, you should get a number that's pretty close to like 1.6. And then the further out you go, you take the next two numbers, make the ratio, next two numbers. What happens is that the ratio of these numbers converges to an irrational number, 1.618, dot, dot, dot. It keeps going forever. It's like this perfect ratio where this side is 1.618 something, and this side's 1. And if you make your rectangle exactly like that, then it's like the perfect rectangle. That's what the Greeks were, right? So these are called perfect rectangles or golden ratio, golden spiral. Got it? Okay, so this number, since it's so special, we have a Greek letter for it, right? Just like pi and e, we have special notation. So the notation we use is that right there. Anyone know what that Greek letter is? Phi or phi. You can call it phi or phi. People argue about that as well. Okay, it's lowercase. So when you see this, in math, we're talking about the golden ratio. So, my story, I'm already wasting too much time. My story is, I have a colleague here who's been teaching here for teaching the Alamo colleges for 50 years. 50 years. So I like working with wood, so I made this for him, and my colleagues thought it would be cool if I shared some of the things about this. So obviously, that's the fee, right there, golden ratio. It's 50th anniversary is usually the golden anniversary, so we went with the golden ratio as the theme. And so I made this wooden little fee. But what's really cool about it, and you can look at this if you're interested after class, do you see all those little dots? Can you see all those little dots there? It's hard to see from the back, but there's like these squares or rectangles. Do you see those rectangles behind this thing? Okay, so there's tiny little dots which are laser engraved in here. And each rectangle here represents 1 year of teaching, and each row has 25 dots, and there's 13 rows. So class is about 25 students, and we teach 5 classes in the fall, 5 in the spring, and usually 3 in the summer. So this top square is 1 year, and then there's 10, and then there's 5 across. So each one of these represents a decade, right? So these dots are just all his students that he's had over the entire, 50 years, right? Approximately. It's like 16,000 something or, okay. That's not the coolest part to me. This is all made using the golden ratio. So this, whatever this is, divided by this, is 1.618. And every rectangle you see on this, if you take the ratio, is 1.618. So anyway, it's kind of cool, huh? Yeah?
Those curves follow the golden ratio?
Do the what?
The curves
On the actual symbol, no. No. Yeah, that's a good question. No, that's just a generic symbol, because the Greek, the letter was actually not part of the golden idea. The Greek letter existed first, right? So they just used that to represent it. Would have been cool if they said, hey, let's change it so it looks like the spiral. But okay, that was completely random, useless information. Yeah. Yes. What? Dr. Dennis Gittinger. I doubt any of you have had him, because he kind of at this point teaches more of the, he teaches like the contemporary math. He used to do all the higher stuff, but then he's kind of backed off over his career, and he just does like contemporary math, like math for the real world, like calculating amortization tables for mortgages and things like that. Yes? The what?
The bonus problem.
What about it? What are you saying?
The bonus problem?
What about it?
Any update on it? Anybody get it? Or?
Yeah, no, I think I said last time, right? 2. Yeah, I think we're at 2. I think 3 people got the first one and 2 have got the second one. I haven't done any grade adjustments though. I'm going to do it for exam 1, the midterm. I'm going to add the bonus there. Okay, we need to get down to business. Where is it? We almost finished last class. We were talking about the directional derivative, right? The directional derivative, this idea that you could be on a surface, point in some direction, take a step, and figure out what that slope would be. And then we looked at this thing called the gradient vector, and we were amazed at the idea that the gradient vector somehow will tell you which direction to point in to have the steepest descent. And we did this example, right? And that's where we finished class. You all worked together on your own, whatever. Y'all worked and did that. So the last thing on this section is the tangent plane formula. So before I put that up there, I want to remind you that in a previous section, where is it? Here we go. Here's 11.4. In this section, 11.4, we talked about tangent planes to a surface, and we said if z is a function of x and y, right, if we have some sheet blowing in the wind, right, somewhere it's fixed, and we want to find the equation of the tangent plane, here's the formula for it. And remember, you asked about this -1, remember that? And I said, hang on, I'll talk about that later. This is how we found tangent planes whenever our surface was a function of 2 variables. In other words, you could solve z equals and then get all the x's and y's to the other side. In this section where we are now, we get a more general formula, okay, which does not require that we have z as a function of x and y. All it requires is that we have an equation that involves three variables equal to a constant. So the equation of a sphere, the equation of an ellipsoid, the equation of any of those quadratic surfaces we looked at, as long as we've got all three variables in an equation, we can find the tangent plane to that surface at some point by doing this computation here. So remember, our generic equation of a plane, this is our generic one, way back at the beginning of this class, chapter 10. That was our generic formula where x naught, y naught, 0 was some point, right? Some point on the plane. And then a, b, and c, remember that was your normal vector, right? That look familiar, everyone? Yes? Okay, so all that's changed here is that this right here is the partial of that f with respect to x, evaluate at the point. This is like the a. And then the b here is this part, and the c is this part. So we use the partial derivative to get our normal vector, and then once we have the normal vector, we already have the point, we go find the equation of the tangent plane. Now, this will answer your question about the -1 in just a moment, all right? I'm sorry, I'm getting over something I had over the weekend. I'm not sick, so here's our first example. Find the equation of the tangent plane to the ellipsoid x squared over 9 plus y squared plus z squared over 25 equals 18. So notice that this looks like some function of three variables equal to a constant. Oh man. It comes in waves. I'll get over this. I'll be fine for 15 minutes and it'll come back. All right. So in order to find the equation of tangent plane, what I need to do is, first I'll write down what is the function of the three variables. That's just the left side of the equation. And now what I'm doing is I'm going to take the partials, first with respect to x, then y, then z. Once I do that, I'm going to plug in the point that I'm given into each of those partials, and that's going to generate the normal vector for the plane. So my partial with respect to x, this is a pretty straightforward one, because this one, all you have to do is bring the 2 down, right? And it's just 2 over 9 x. And then the partial with respect to x, these two are both 0, because they don't have x's in them, right? So you treat the y like a constant, you treat the z like a constant. They go away. Then the partial with respect to y is just 2y. And then the partial with respect to z would just be 2 over 25 z. Would you all agree that's a pretty clean partials there? Nothing crazy? All right, now what I need is to figure out what the value of these partials are at the point I'm given. So the partial of f with respect to x at the point -3, 4, 5 would be equal to, well, all you're going to do is replace x with that, y with that, z with that, right? But all you have in the formula is an x. So just replace x with -3. We should get -2/3 there. Okay, just plug in -3 right into this. Now I do the same thing for the next two. Okay, so all I'm going to do here, since this equation just has a y in it, 2 times 4 is 8. And then finally here, 2/5. All right, there it is. So that's basically my normal vector, right? That's the normal vector for the plane. So I'm just going to go to the equation of the plane, or make the equation of the plane now. And what I'm going to do is I'm going to start by taking this number, -2/3, and then parentheses x minus x naught, but x naught for us is -3, right? So I'm going to go minus -3, which is plus 3. And then plus now the y component of the normal vector, which is 8, in front of y minus y naught. Y naught for us is 4. And then finally, plus the z component of the normal vector, which is 2/5, and then z minus 5 equals 0. And that is the equation of a plane. And that plane in particular is the one that is tangent to that surface at that point. And to verify it visually, I've actually drawn the ellipsoid here. And you can see on this ellipsoid that point I'm representing there in black. And if you click here to graph that plane, you can see that that plane is tangent to that surface at that point. Any questions? So as long as you can take the partials and evaluate the partials at the point, you should be able to come up with a tangent plane, right? Now, let's answer that question back in 11.4, or 11-4. Why was this formula so similar, right? Partial with respect to x, partial with respect to y, but why was this not partial with respect to z? Why was it -1, right? Why? Well, here's why. Because, let me leave this up here. Because if we go back to what we did before in 11.4, we were saying that z is some function of x and y, right? But here, what we need is, we need a function of x, y, and z, right, equal to a constant. So what I'm going to do up here is I'm going to subtract z from both sides. Now, do you all agree that this is an equation? It's equal to a constant. In the right-hand side, I could look at this as being some capital F that depends on x, y, and z, right? Like you give me x and y, I can give you that. You give me z, I can give you that, right? So all I need is x, y, z to figure that out, yes? So now what I do is I take the partials, right? Just like I did over here. So if I take the partial with respect to x, well, that part will be the partial of this with respect to x. Well, this is going to go away, isn't it? Because that's just z. So that's a constant, so derivative of that's 0. And what's derivative of this with respect to x? Well, I don't know. It's whatever the partial of little f is with respect to x. And then if I want to know what the partial of f with respect to y is, capital F with respect to y, again, the derivative of this will go away because it's a constant. And I need to know what the derivative of that is with respect to y, which is, I don't know, something, right? But here's the big part. You see it? What's the partial of capital F with respect to z? -1, right? -1 because that right there, this right here has x's and y's, right? There's no z's in here. So when you take the partial with respect to z, you treat all of that like a constant. The derivative of that goes to 0. And then that is z, so the derivative of z is 1, but then it's subtracted, so you get -1. So you see how that formula in 11.4 is basically the same thing, except that whenever it's solved for z like this, you can always do this step, which means you're always going to get a -1 down there. Hope that makes sense. Does that answer the question? Okay. All right, that's it for that section. Okay, that's it. Oh, no, that's not. Hold on, there was one more thing. Hold on. This looks like the same question, but it's not. Let's read that carefully for a moment. Find the equation of the what? Normal line to the tangent plane. So the reason I'm doing this is because I have not discussed what a normal line is to something. So let's take a look visually, and then we'll see how we're going to do it. Here's that same ellipsoid, and we had found that plane, hadn't we? We had found that plane that was tangent to it at that point. The normal line is the line that goes through that point, but is orthogonal to the plane, perpendicular to the plane. That's called the normal line. So if you give me a sheet, right, a plane, and I want to find the equation of a normal line, that would be any line that is orthogonal to this, anywhere. But I want it to also go through that point, right? So for this problem, if we're trying to find the equation of the normal line, how do we find the equation of lines? What do we need? Yeah, so to find the equation of a line, we need a vector, right, which gives us like a point. And then we need to add to that t times v, where v is the direction vector of the line. Well, do we have the point? Yeah, we do, right? That's the point 3, 4, 5. So I'll turn it into a vector. Plus t times now. Do I have the direction of the normal line?
You kind of do, yeah.
How?
Yeah, it's going to be perpendicular.
The vector we found earlier, right? That normal vector for the plane, isn't that by definition, that vector is orthogonal to the plane? Which means that it would point in the same direction as our normal line. So in other words, we just need to use the same vector that we got, the A, B, C that we just got in the previous problem. What were they again? Was it negative 2/5?
Negative
2/3. 8 2/5. There we go. That right there would be the equation of the normal line. And that's it, we're done. If I asked you for the equation of the tangent line here at this point, you could not give me a unique answer, right? Because if you think about that tangent plane, right, that tangent plane that's sitting here, right, here's that tangent plane. If I say find the equation of the tangent line at that point, well, there's an infinite number of lines that go through that point, right, that are all tangent to the surface. So the plane is a better definition than a tangent line when you're talking about surfaces. Now, there's only one normal line, but there's infinitely many tangent ones. So I would never ask you for that. But if you're wondering, well, why is he asking for the normal, not the tangent? Well, that's why, because it would be impossible for you to really give me an answer. Or a unique answer. All right, moving on. All right, I want to do I thought about whether or not I should do this, but I'm going to do it. I want to do a recap of something that you saw in Cal 1. And I know if you took me for Cal 1, I didn't emphasize this too much. So I'm just going to lay it out here, all right? Recall from Cal 1 that we can find, or I'll say finding local max and local min of functions. Now this would have been very useful on your most recent mini exam.
Yeah.
But I wanted you to go back and refresh. All right? I didn't want to have to like hand feed it to you. So finding local max and mins of a function. If you're given a function, let's say, I don't know. Well, let me lay out the idea here. Local max and min means we're trying to find the hilltops and the valleys, right? Where are all the hilltops and valleys of a function? We have this thing called the second derivative test. Like I said, in my Cal 1, I don't get into this too much. Something called the second derivative test. So what it does is it says this. Let's say it says, suppose, have y'all seen that symbol before? Capital S with a little line like that? That stands for the word suppose. All right, I'm not making that up. That's mathematicians, we use that, okay? Suppose f prime of c equals 0, all right? What I'm telling you is, let's say that you've got some function. I'm just summarizing this test. There's a more formal definition of it in the textbook. But it says, let's say that you have some function, and when you go to the value of c, the derivative is 0. Okay, so I'm going to draw you that picture. I go to some value c, and here's what I can tell you. On that function, whatever the function looks like, the derivative is 0, which means that the slope of the tangent line is flat. So that red represents my tangent line being flat. Understand? Yes? So suppose this is true. Then, if f double prime at C is a positive number, what does the second derivative tell you in Cal 1? About what? First derivative is where it goes up and down. What does the second derivative tell you? Concave up or down. Concave up or down. Right? So if your second derivative is positive, you're concave up. Right? So imagine you have your first derivative there is 0, and your second derivative tells you you're concave up. That means your graph would have to look like that there, right? So that blue represents the kind of the concavity of the function. Do you all agree then that this point must represent a local minimum? Yes. There's only one way that I can draw this. No matter what's happening over here, if I have to come down and then back up like that to be concave up in a flat tangent, that has to be a local minimum. So if the second derivative is positive there, then if this is true, then f of c, the function's value at c, is a local what? Minimum. Local minimum. I'm not saying it's the absolute minimum, the lowest point on the graph. I can just tell you that it goes down and back up there. Is it important that this is equal to 0 and not, what's the other thing that can happen with the derivative? Derivative can be 0, sometimes it can not exist, right? Like at a corner or a cusp. This second derivative test does not help you if you have a corner or a cusp. Because if you have a corner or cusp like this, like that, do you all agree that that's still a local minimum?
Yeah.
Yes? But the second derivative test won't catch it because you need to have first that at this value of c, you need the derivative to be 0, which it's not. At a cusp, it's undefined, or the limit doesn't exist. So you won't be able to find this with the second derivative test. Does that kind of make sense to you? So that's why my Cal 1 students, I don't do this test, because the way we do it is, in my Cal 1 was we said, okay, figure out the critical numbers, figure out if the graph goes down and back up, then you know you have a minimum. Or if it goes up and then down, you know you have a local max. So anyway, that's off the side. That's off the side. All right, that's the first case, right? What about if it's the other way around? If your derivative at c is 0, but your second derivative is negative, then what? You're a local max, right? So the picture of that would look like this. You have at c, your derivative is 0, but now if your second derivative is negative, you're concave down, and so your graph must go like this. So this would be a local, that's L, local max. This is a local min, right? So if this is the case, then f of c is a local min. All right, yeah? Cal 1. Now, we're going to do kind of the same idea here, but with surfaces instead of flat